Welcome back. This is the second lecture of the third week. Today we are going to discuss one of the very important components of demand side management, which is called the load management. As you know, we are discussing about the energy demand under module 2, and today we are going to discuss about load management. Let us start with the concept of load management. What do we understand by load management? This is basically a sustainable management of the amount and or the timing of customers' use of energy. And this is specifically used in the context of electricity consumption. In the last lecture, you have already been introduced to the concept of the load curve, and today we'll take a tour to understand in detail what load curve actually means. Let us start with the concept of load curve. So this red line that you can see here, this red line that you can see here, this is actually tell you at every point of time, at every hour, what is the total consumption of electricity of a particular household. So basically load curve is a depiction of the demand for electricity over a period of time, and it captures the consumption pattern, the amount as well as the variation of electricity consumption. Now, whom do we derive the load curve for? That is the question. So, load curve can be derived for a particular residential customer. It can also be derived for a particular locality, or you can also derive this for a particular country. So, you can go from a very micro level to a very macro level load curve for understanding various concepts and understanding various demand patterns. It depends on what is the question that you are trying to answer. So if we look at this load curve that has been depicted here, you can see that at 1 a.m. in the morning, the consumption of electricity is approximately 18 kilowatt hour. It remains between 60 and 18 kilowatt hour up to the morning time, which is up to 6 o'clock. After that, there is a sharp peak that you can observe here, and suddenly the energy consumption goes up to almost 150 to 160 kilowatt per hour. But this is a very sharp and short peak. This does not stay longer, and after a while it comes down, and then you see a valley kind of the curve here, which we call the off-peak period. So this off-peak period is actually prevailing between almost, I can say 10 a.m. in the morning till 4 p.m. in the afternoon. So this is a valley where you see the off-peak demand. Again, there is a peak where the energy consumption, or I should say the electricity consumption, increases for this particular residential household, and it stays more or less high, and then again it comes down, and then you again go back to this kind of valley. So you can see that there are ups and downs in the electricity consumption during the day during a day for a particular household. So although we say we can think about an average electricity consumption per day by a particular residential sector, but it doesn't mean that during the entire day the electricity demand remains the same. In fact, what we can see, it fluctuates quite a lot. And that is why what we have said here is that the load curve is a depiction of demand for electricity over time. It gives you the pattern as well as the variation. Now let us have a quick look to understand what can be the causes of the peak and off-peak period for this particular load curve. So one point of caution is that the explanation may vary depending on the type of household that you are talking about, whether you are talking about a locality or you are talking about a country, and so on. So it's not fixed, it's not written on the stone. So these can be one of the explanations out of many explanations. So you see that the peak period of this particular household starts at around 7 a.m. So it may consist of a number of family members who are going out for some offices. So they all are working, children are going to the school. So in the morning there is a lot of demand for electricity for cooking, maybe the washing machine, for water motor, water geyser, and so on. So this can be various reasons why there is a short and sharp peak. Once these activities are done, they all leave for the offices or the schools or for some outside activities, and therefore there is hardly any electrical equipment that is on in the house. And therefore there you see a prolonged valley or prolonged off-peak period for this particular household. So basically the office hour duration coincides with the off-peak period for this particular household. So everybody has left for work. Now you can imagine people started coming back in the evening, late afternoon, evening, 4, 5 o'clock, and then the rest of the activities again start. Maybe space cooling. If this is, summer, then it's space cooling, lighting. People maybe they are engaging into some entertainment activities, and that again require a lot of electricity. So again, you should see sort of a peak period. But there is a difference between this peak and this peak. This is a very short and sharp. So there are a lot of activities happening intensively in 1 hour. However, this peak is kind of prolonged, right? So this is not as sharp as this one, and this is a bit kind of prolonged. So there are variation in the peak demand as well. That too again may not be uniform. It may vary from household to household. Now let us try to understand this can be the explanation for peak and off-peak period for a particular household, but what can be the explanation for having the peak and off-peak period for a particular locality, for example, the municipality corporation. This is something we had discussed in the previous lecture. So you see that during the morning period, the municipality corporation may actually experience a hike in demand for electricity for various activities, one dominating activities being the water pumping in the city. Then it might have a valley where there is no water pumping, and this is during the daytime, so you don't also require the electricity for street lighting. But after a while, if as you approach the night time, you switch on the street lights, and then again the demand for electricity goes up. So there can be various explanations why you are having a peak load and why are you having the off peak load. So what are the electrical equipment that you are using during the peak load period, and what are the electrical equipment and activities that you are carrying out during the off peak period. So understanding of this particular thing is very important in the context of demand side management. So this is the foundation of demand side management, to understand the load curve and also to understand what causes this particular shape of the load curve. Before I go into the next slide, I would like to draw your attention to one particular term, which is season. So although we are saying that this is the load curve for a particular household, there can be variation in the shape of the load curve from day to day. Not only that, the variation can be actually significant if you think about two different seasons, right? So the load curve that you see, the peak periods and the off peak periods that you can see, or the height of the peak that you can see during the summer and the winter may vary significantly. So in this case, we are saying that in the evening time, people may be using space cooling equipment, and therefore you get another peak. But if you think about the winters, then there is no space cooling activities going on, and therefore in the night time, you can have an even sharper decline in the electricity demand, generating a deeper valley. So I mean, all these points, it actually shows you how important it is to understand the load curves at a disaggregate level. Next, the point that we are going to discuss, why is it so important to have a flatter load curve where you have less difference between the peak hour demand and the off peak hour demand. You will later see that this is the main objective of the load management, one of the main objectives of load management. So if this is the existing demand curve, this is the demand curve in the reference scenario that you have, in order to supply this much of electricity, you actually need the power plant whose size is big enough to meet this electricity demand at the peak period. So the size of the power plant that we want should be commensurate with the size of the peak demand. Otherwise, there will be a power cut during the peak demand. So this is the size of the power plant that you actually need in order to support this kind of a load curve. Now see what is happening. During the off-peak period, the demand is pretty low. It's much less than what this plant can actually produce. Now, if the off-peak demand is lower than what the plant can produce, of course, the plant can reduce the supply of electricity by keeping some of the units non-operational, non-function. But in that case, what is happening? This is the amount of, or this is the capacity of the power plant which remain unutilized during the off-peak period. Now, why are we so concerned about the unutilized capacity in a power plant? because you need to understand that the investment in power plant is very, very high. Therefore, if you have a big power plant and during the most of the time of the day, most of the part of this power plant remain unutilized, that means that a lot of investment that has gone into the setting up of this power plant, it remains unproductive. And this is a very, very important scenario in the context of a developing country where you have various sectors who are demanding a lot of investment. So when we were talking about consumers and producers optimization behavior, we said that those are constrained optimization. So the consumer is working within the constraint of a budget space. If you think in the context of a state or of a country, the country also has a constraint optimization problem where it has a limited amount of money. There are diverse requirements for investment, and this is one of them, to invest in the power plants. And therefore, if you are investing in a power plant, you are actually not investing in certain other development activities. Now, the amount of money which you are investing in power plant, that is huge, and if a major part of that remain unutilized, then you can imagine this is not a good way to invest. This is not a way in which you can get the maximum productivity out of your investment. And therefore, it's very important that this part, this unutilized capacity needs to be minimized. So this is one of the objectives. If you want to do that, what is the way of doing that? Basically, you see, if you shift some of the load from your peak period to the off-peak period, you will probably require a plant size which is smaller, and not only that, your unutilized capacity, the size of your unutilized capacity will become smaller. Let us have a quick look what we are trying to say. So in the reference scenario in this diagram, if you have a load curve like this is the plant size that you require, and this is the underutilization of the power plant that you have in place. Now suppose we keep the total daily demand for electricity constant. So if you look at this blue line and this red line, basically if you add the electricity consumption for these two lines for different hours, for 24 hours, you will see that it represents the same amount of electricity being consumed. However, what is the difference? The difference is that from this red curve, the peak of the blue curve is much lower than the peak of the red curve. So the peak happens somewhere between 155 to 160 kilowatt hour in case of the 60 kilowatt hour in case of the red line. However, if you look at the peak here, it's close to 120 kilowatt hour. The other difference is that if you look at the valley, that is the off-peak period, here the off-peak demand goes down even below 60 kilowatt hour. Here the off-peak demand is not that low. It hovers around between I'd say 60 to 80 kilowatt hour. So the peak has come down here, and the valley, that is the off-peak, has gone up. How has that happened? Actually, some of the loads that were occurring at this part has been transferred to the off-peak period. That is how the curve has been flattened. Now, why is it so important to have a flatter, load curve? This is the question. It's because of this reason. If you think of this blue load curve as compared to the red load curve, it says that the consumer is consuming the same amount of electricity. So there is no curtailment in terms of the total electricity consumption of the consumer. However, earlier the plant size that you required was this. Now, in order to support the peak load, which is around 180, the plant size that you actually need to operate is here. So basically, there is an avoided capacity that you can see. So instead of investing in a bigger plant, you can actually invest in a smaller power generation plant, and this difference is going to be huge because setting up power plant itself is highly cost intensive. There is a second advantage. What is that? There will be a gain in efficiency. During the off-peak period, if you see here, this was the amount of underutilization of the power plant. The underutilization actually comes down because of two reasons. Now your off-peak demand has gone up and your plant size has come down. As a result, there is a squeezing of this particular red line to this particular red line here, which shows a lower underutilization and the higher economic efficiency of your investment. So this is the kind of bottom line why we want to have a flatter load curve as compared to a load curve which has very deep off peak demand and very high and sharp peak demand. Other than shifting load, there are many ways the load can be managed. So this is about the management of load. We'll have a quick look at 6 of them. First, to start with peak clipping. So if this is the load curve that you have, this is the peak. And as I have said, it's very important to have a lower peak because that determines the size of your power plant, right? So you want to reduce the peak. How can you do that? Suppose in the morning there are a lot of activities at around 7 a.m. which is going on, the geyser is switched on, there are cooking activities going on, heating of the food and other things, maybe the water pump is on, several activities are going on. So that is giving you the peak. Now the question is it possible for the consumer to switch off the refrigerator for 1 hour during that period? Or is it possible for the consumer to actually increase the temperature of the refrigerator during that period? If that is possible, then you will see that there is a reduction in the peak demand. So that is what is called peak clipping. The second one is valley filling. Why valley filling is important? Now again we have an understanding. If the valley is, if we can fill up the valley, then the part of power plant which remains underutilized, the capacity which remains underutilized will come down. Therefore, it's important to have valley filling activity in order to increase the efficiency of the whole investment system. How can valley be filled? So some activities can be undertaken at night or during the periods when you have very low electricity consumption. A more plausible option is actually a combination of peak clipping and valley filling. This is the reduction of utility loads during the periods of peak demand while at the same time building the load during the off-peak periods. So load shifting typically does not substantially alter the total electricity of the cells. What you have observed that the total electricity use and sale remain more or less unchanged in case of the red load curve and the blue load curve. However, the shape was very different. So if you combine the peak clipping and valley filling, and this is one of the most important strategies under load management, what you get is called a load shifting. So basically you are shifting your peak hour load to off-peak hours. So let me give you a quick example. Suppose you want a lot of hot water for bathing in the morning for the whole family and you have a storage geyser in place. So instead of switching on the geyser in the morning, you can actually switch on the geyser at night where you are having some off-peak demand and let the water heated and then just let it be stored in the geyser and use it in the next day morning. So this is a typical example of load shifting. There are various other examples of load shifting as well, and this is actually studied deeply in the context of load management. Another important strategy of load management is called conservation. So conservation is basically the reduction in utility loads more or less equally during the entire period of day. So here in this diagram you can see that there is almost a parallel shift of the load curve downward. When does this happen? This is actually evident when you employ some sort of energy efficient equipment in place. So energy efficiency is one of the main reasons behind having this kind of conservation activities. And energy efficiency, we can consider this to be a part of load management, or broadly what we say that load management and energy efficiency are two pillars of demand side management. However, in the literature, you will see this load management, energy efficiency, demand side management, all these concepts, they are used interchangeably. They actually go hand in hand, and all of them, they act together in order to achieve the demand side management. The next one, so this is the fifth one that we are going to talk about, is load building. As we said, for energy conservation, the entire load curve shifts downward. Here, the entire load curve will go upward. Now you might be very surprised to see that here actually the energy consumption is going up. However, that is also very important if we are talking about places where people do not use enough electricity, which is important for their sustainable development. Therefore, building up the load is also load management. So again we come back to the point, this term management, which is very, very important. So management does not simply imply the reduction. Management means how can you optimally use a scarce resource. So this is again the optimum utilization of scarce resource, a resource that you use in the best possible manner. It does not mean that you deprive somebody and you ask somebody to reduce the consumption to such an extent that the sustainable development is hampered. So load building can also be a component of load management, especially in the context of very developing countries or less developed countries. The last one that we are going to look at is called the flexible load share. This is something which is not quite available in our country. This is actually based on a contract between the utility, that is the power supplier, and the consumer. So what do? They enter into a contract, and it kind of, the utilities actually install certain instruments or some equipment in order to alter customers' energy consumption on as needed basis. So the utility itself will actually have a control over different electrical equipment that has been installed in the customer's place. Okay, and if the utility thinks that there is some very peak demand is approaching, then they may disconnect the use of those particular equipment. Now this is especially useful if you are thinking about activities such as washing machine, so washing the clothes. This doesn't have to happen in a particular time of the day, but the activity can be shifted at any point of the day, probably to it has a kind of flexibility. So usually the customers, what they do, they register with this program with the equipment whose use is flexible during the time of the day. However, this is not there in our country. In many of the developed countries, you see that this is in place. Let us have a quick look, and this is the fun exercise that we are going to do. We'll take a couple of examples and we'll try to see which load management concept we can attach to this particular event. The first one is universal electrification in India. So what I would suggest is that before you listen to what I am saying, after each option comes, you can pause the video for a while and you can think about a bit which option would you actually like this particular event to attach to, and then we can see that whether our opinions match or not. So we begin with universal electrification in India. So it's sort of simple. When you have universal electrification in India, you are providing electricity to a lot more households, and the load curve is going to go up. So this is definitely a load building activity. Again, to emphasize, this is also a very important part of load management and the demand side management. The second one is buying an electric vehicle and charging it at night. So electric vehicles run on battery and you have to charge these batteries. You have to have a charging infrastructure in place, and it's up to you when you want to charge the battery. Now see the option that I'm giving you, I'm saying that you're going to buy a new electric vehicle and charge the batteries at night. So this activity was earlier not present in your electricity consumption profile, but now this is going to be added. Now if assuming that night time is your off-peak period, if you carry on this activity in the off-peak period, then you are contributing to valley filling, so that your rest of the load curve remains unchanged, whereas you are actually increasing your energy demand during the off-peak period. Coming to the next one, replacement of incandescent bulbs by LED. Well, there are two options that you can choose. If you think about replacement of incandescent bulbs by LED in a particular commercial area where the lights are always on, this will actually lead to conservation. So you are actually reducing your energy consumption at every point of time. However, if you think about a particular household or the residential sector, probably the demand for lighting service comes during the evening, late evening, night, and so on. So if that period is the peak demand period for the residential consumer, then replacement of incandescent bulbs by LED will actually lead to peak clipping. So during the peak period, your demand is coming down. Nothing happens to the rest of the time where you actually do not have any requirement for uh, uh, lighting services. So there can be multiple options as well. Next one is installation of solar street lighting. So this you can see that if the solar street lights are installed, then in one particular peak demand period, which is the evening peak demand for the municipality corporation, the electricity demand from grid will come down. So this is another example when you have peak clipping. And with the help of this example, what you can see is that if you have demand side management in place, you are actually encouraging, or you may encourage the consumers to install the renewable energy systems in a scale that is feasible within their domain. So this is an example of that. The next one is uninformed power cut and informed power cut. So I have deliberately kept two options. One is uninformed power cut and the other one is informed. Now see, if let us take an example of uninformed power cut. Suppose you take your dinner at 8:30 p.m. and there is a sudden power cut at 8 p.m. which continues till 9:30. Now you had no prior information about this power cut. What do? You are forced to eat the cold food, right? If that happens, you can say that, and if this happens during your peak demand period, then you may suggest that, see, this is an activity which is leading to peak clipping because your energy demand in the peak period has been forced to come down. Okay. However, I would like to recommend that it's better not to call a peak clipping, because this kind of an event is not at all sort of an load management. So the concept of management is highly related to informed decision making. You know about something and you are optimizing based on that particular information. Here you had no information. You were forced to do something which you would not like to do. So this should not come under the load management at all. This is an unprecedented event which should not happen again. However, if there is an informed power cut, so see, the in power cut, if it is not because of some technical fault, then it takes place during the peak period. Now, if there is an informed power cut during the same period of time, that is from 8 to 9:30, and you know it beforehand, what will you do? Probably you will heat your food a while, before 8 p.m. and keep it and have it at your dinner time. So you can manage, or you can alter your behavior. Now this means that when there is an informed power cut, you are shifting some X amount of load from your peak period to the off peak period as you are heating up your food before the peak period approaches, right? So if this is an informed power cut, then you can imagine this is the case of load shifting. The next one, high tariff during peak demand and low tariff during off peak demand, and this is actually lead us to the next slide. This is sort of an incentive structure, and this will lead to load shifting again, because if the price is high, then given the law of demand, people will lower their demand, and if the price is low, people are going to increase their demand. So if during the off peak period, if you increase the price, there will be a tendency of individuals to reduce the demand, whereas if you reduce the price during the off peak period, they'll try to use more during the off peak period, and probably there will be a shift of load from peak period to off peak period, leading to load shifting. In next two slides, we will discuss about the economic incentive for load shifting or demand response. This is the definition, or this is the line from US Department of Energy. This says that changes in electric usage by end-use customers from their normal consumption pattern, remember the red load curve, in response to changes in the price of electricity over time, or to incentive payments designed to induce lower electricity use at times of high prices or when system reliability is jeopardized. So in a way, this is actually talking about the high tariff during the peak period and low tariff during the off peak period, or similar kind of incentive. Now you will find interesting that I have taken this kind of statement from US Department of Energy, and not from any other developing country, because it's often discussed that load management, the concept of load management or load shifting, is more relevant and has been more researched in the context of developed countries, because you have a lot of load added to your activities which can be shifted at various times of the day. If you think about developing countries, the equipment that use electricity, the number of those equipment are so low that sometimes your electricity demand at every point of time is kind of rigid, and therefore it's difficult to implement the load management policies. However, there are results which contradict this as well, but most of the literature on load management that you will find it in the context of the developed countries, or in the context of industrial users, the high tension users, the commercial buildings and all. There is in fact very limited literature on load management in the household or residential sector in the developing countries. However, coming back to our point, we were discussing about the economic incentive for load shifting. So you have to build up the incentive in a particular manner so that again people take some informed decision. You are not forcing people to do something, but you are just allowing them to take some informed decision which will flatten your load curve. There can be two types of economic incentive that you come across in the literature. The first one is price-based mechanism. So this basically borrows from what we discussed, high tariff during the peak period and low tariff during the off-peak period. There are various particular forms of price mechanism that you can come across at various parts of the world. Some of the common one are as follows. One is time of the use or time of the day. This is something we have been discussing. Tariffs are charged based on the time of the use. Off-peak period has lower tariff and peak period will have higher tariff to incentivize the load shifting. The second one is called the real-time pricing. So the price changes on an hourly basis, not depending on the peak or off-peak period. There is more, disaggregation. Hourly basis depending on the price in the wholesale price at the power exchange where the electricity is being bought and sold. Now, in both these cases, you see that the consumer can actually take an informed decision if the prices are communicated to them, beforehand. So that is something happens. I mean, you let the consumers know about the price, few hours ahead of time, or maybe one day ahead. So that is again very important. Otherwise, even if you are changing the tariff and the consumers don't know about it, you can expect no result out of it. The third one is critical peak pricing. Let us take the example of Diwali. In the night of Diwali, there is a sudden rise in the electricity demand. So every state, every city, every village, it requires a lot of electricity in order to lighten up the streets and buildings and so on. So critical peak pricing actually means high rise in price due to some critical events like Diwali. So maybe on the day of Diwali, in the evening of the Diwali, there will be an extreme hike or extreme increase in the price of electricity in order to make people taking optimized decisions. The final one that we are going to discuss, and there can be many more, I mean these are not the only 4 types of price-based mechanism, is called the peak time rebate. So instead of reducing the price during the off-peak hour, what it says that if you reduce your electricity consumption during the peak period, there will be a rebate which will be realized in your electricity bill. So these are the types of price incentive that you can observe. The second type is the incentive-based mechanism. It's not actually the price may not change at different points of time, but the incentive structure may vary. Actually, in some of the literature, you will find that this peak time rebate is considered not to be a price-based mechanism, but more like an incentive-based mechanism. So what can be the incentive-based mechanism? The first one is called the direct load control. Here the utility installs a control device on electrical equipment of willing customers, and through this device the utility is able to shut down or cycles the appliances. So this is same as the flexible load management. So the utility can control the use or usage pattern of some of the electrical equipment that are installed mainly in the residential sector or in the small commercial sector. This does not really happen in the case of the industrial sector. The second is called the interruptible load. Here the consumer will generate a part of demand on their own during the peak load with combined heat and power. This is for the industry, maybe through the solar panel, or it may use the battery as well. This is a very interesting concept, because here what you are doing is that you are asking the consumer to become a producer of electricity. So in the peak period, the residential sector, one particular building might say that, okay, we are going to, fix our peak load. We can actually support X percentage of our peak load by the amount of electricity that we are generating through the solar power at our own place. So this way the consumer also becomes a producer, and this particular category in the literature is called the prosumer. And this is a very good example how you actually integrate the behavior of the consumer. You integrate the consumer as a part of the whole electricity network. So it becomes an integrated decision making system. However, when you enter into an agreement with the utilities and you say that, okay, I'm going to support X amount of my peak load through my own generation, then you receive some financial benefit from the utilities. The last one that we are going to discuss is called the capacity market programs. Here the consumers agree to reduce the load to a pre-specified level. So there will be a threshold which will be set up, and the consumer has to reduce the electricity consumption beyond that level. And this threshold is of course more applicable when you are having your peak demand. So if you become a part of this program, then the utilities will make some guaranteed payment. However, if your obligations are not met, if you are a defaulter, then there can be some penalty which will be applied. So in a nutshell, these are the various types of price-based and incentive-based mechanisms that are in place in order to promote load management techniques under demand-side management. Here we are going to have a quick look at these two diagrams in order to understand how we use the economic framework of utility maximization in order to understand the response to this price or the price mechanism. So what we have started with this fact that suppose this is the plant size that you have, the black line is the plant size, and under the reference scenario, your demand for electricity actually higher than what the plant can produce during the peak period. So you can say that during the peak period there is an excess demand for electricity. If there is an excess demand for electricity and you want to discourage the demand, then you can increase the price. The utilities can actually increase the price. If the price is high, then in a two commodity framework where in the x-axis we are plotting electricity and in the y-axis we are plotting all other goods, we can represent the budget line during the high price as this. So this budget line represents the budget line for the consumer during the peak period, resulting to the equilibrium at E0, and Q1 is the quantity of electricity that is demanded. However, you can also see that during the off-peak period, there is a kind of a excess supply. This is not excess supply in terms of the fact that the power producers are producing and supplying this particular amount of power. So they may reduce their supply of power. But in terms of capacity utilization, there is of course some kind of an excess demand which you want, excess supply which you want to reduce. If you want to reduce that, we can actually reduce the price of electricity, which will increase the demand during the off-peak period. If the price of electricity is reduced, then the budget curve for the line for the consumer actually rotates. So if the black line represents the budget line for the consumer during the peak period, and this is the budget line for the consumer during the off-peak period. And the equilibrium also shifts from E0 to E1, resulting an increase in the electricity demand during the off-peak period. So this is how the dynamic pricing system can actually reduce the consumption of electricity during the peak hour and increase demand for electricity during the off-peak hour. Now, one note here is that this kind of dynamic pricing is not prevalent in India for the residential customers. This is there for the high tension users, the industry sector. It's also applicable for the commercial users, but it's not there for the household sector. What we have in the household sector is more like a block pricing. So up to X amount of, up to X unit of consumption, you pay a particular price. If your consumption goes beyond that, then you pay an increased price. So as your consumption during the month increases, in different blocks you pay different amount of your price per unit actually increases as your consumption increases. But that is not really the dynamic pricing. So you should be able to distinguish between the dynamic pricing, where the price is changing in a day, and the block pricing, where the price that you pay for different levels of consumption of electricity are different. There are various things that you have to especially the policymakers need to keep in the mind while implementing the load management policies. So it's not as easy as it seems like. So I have taken this example from a paper that we'll discuss in a while. So this is basically the load curve for a particular locality, and you see that there are two peaks which are observed for the residential sector. The peak period starts from 6 a.m. in the morning and goes until 11 a.m. in the morning. So 6 to 11 a.m. is one peak for the residential. So this is the aggregate demand curve for the residential sector, or aggregate load curve. And the second peak that you observe, this is again from 6 to 11 or 6 to 10, but in the evening. So these are the peak demands. Now the question is that, is it the case that industrial peak hour also coincide with the peak hour for the residential consumer or not? This question is very, very important, because if the peak period or peak demand for the industrial consumer does not match with the peak period of the residential consumer, and if you incentivize the residential consumers in order to shift load from peak to off peak period of residential sector, then it may actually add to the total load of the peak period of the aggregate demand curve, because the aggregate demand curve is a result of aggregation of the load curve for the residential sector as well as the non-residential sector. Maybe this illustration will make things more clearer. We are taking an example where these shaded periods are the peak demand for the high tension users, that is the industry and the commercial sectors. So their peak period actually coincides with the peak period of the residential sector. If that is the case, then this peak period, that is morning 6 to 11 and evening 6 to 10, this is the period where the load coming from the residential sector as well as from the high tension sector both are high. So the load in the peak period in an aggregate level is very, very high. Another thing you have to keep in mind, the load curve that you are having for the high tension users, this is in response to the dynamic pricing. So they are already facing the dynamic pricing. So their kind of load distribution is kind of stable. However, if there is overlapping of peak load for the high tension and residential users, and you sort of introduce the time of use or time of day, so that the residential sector transfers some of this peak load to the off peak period, that will actually add to the off peak period in an aggregate. So this is not only the off peak period for the residential, this is also the off peak period for the high tension users, and therefore this is the off peak period in an aggregate. So if the residential peak load and the industrial peak load more or less coincides or more or less look similar, then only it makes sense to incentivize the household sector to shift their peak load to some off-peak period. Otherwise, it may create some other problem. You can have a detailed discussion on this if you go to this paper published by Thakur and Chakraborty in the year 2016. It gives you a detailed understanding of different types of demand management policies that are applicable for developing countries, how the price mechanism is structured in India, and what can be the responses. We are actually going to discuss a little bit about this paper, some observations that has been found, and it's important in the context of load management. So this study was carried out so the data for this study was actually collected in the year 2013-14 for a duration of 1 year in some urban locality in a union territory where 97 smart residential meters were installed. So they generated data from 97 smart meters installed in the residential area. Now we are introduced with this new term which is called smart meters. So we'll take a short digression and quickly look at what do we mean by smart grid and smart meter, and what are the roles of these things in the context of demand side management. So smart grid is basically an automation of electric grid with ICT, that is integrated information and communication technology, which aims towards the efficient management of the electricity network. So this integration of the ICT is very, very important in the context of smart grid. And smart meters, these are the components of smart grid which are installed to each and every household, which are coming under the smart grid to generate a lot of data and to have a clear understanding of the load curve for each of the households. Now, if you think about your home, in most of the cases, you will see that a person comes at the end of the month and he or she notes down the difference between the units of the previous month and the current unit. So you get only one figure for the entire house where the electricity, which will be covered by one electricity bill, and it doesn't tell you what is the load curve, right? You don't get a detailed information. So the smart meters are a component of smart grid where you are getting information on electricity consumption at every hour of your day. So you basically get the load curve. So you can imagine for this particular study, they were getting 97 load curves per day for each year of the day. So if it was run for 365 days, or 365 days for 97 residential units, they were getting 365 multiplied by 24 multiplied by 97 use points. What does it do? First of all, it generates a lot of data, which is very, very important in order to understand what your demand side management can deliver and what should be the actual pattern of incentive. The second, it integrates the role of consumer in the whole system, and it shows the way towards some kind of financial saving to the consumer. The other thing is that this we have already discussed, that this leads to avoidance of the investment in additional power generation activities. So this investment can go to certain other development activities. And later we'll see this can also integrate the renewable in the whole system. So if you can, through this whole smart grid system. So coming back to the study, based on this data collected from these 97 smart meters, what they have done, they have run a simulation to study what is the impact of two mechanisms. One is time of use and the other is incentivized load limiting. And they are trying to look at the impact on two things. One is the impact on the load curve, and the second is the impact of the financial saving of the residential household. See, as a consumer, I am not really interested in the load curve, right, per se. What I am interested is in the fact whether I am getting some financial saving by acting in a particular way or not. So in the time of use, you can see that there is a higher price, higher tariff for peak period, a medium tariff for the mid-peak period, and a very low tariff for off-peak period to encourage the consumers go for load shifting. And what they have seen is that if you can include more and more customer to participate in this program, then not only the shifted load will be higher, but also the financial savings altogether will be higher. And they are taking help of two parameters, AP and LS. AP is the amount of demand of electricity greater than average demand of electricity during peak hour, and LS is the amount of load to be shifted from peak to mid-peak hour. And then they show what under different combinations of AP and LS how the load curve changes. Now, one interesting observation, if you go through this paper, you will see one interesting observation is that you have to really intelligently choose AP and LS, because if you have if you are setting up your incentive in a not in a right manner, if there happens to be a lot of load shifting, then instead of flattening the load curve, you may end up having a new peak during the off peak period. That is also possible. So this kind of simulation actually gives you an idea what should be the optimum tariff structure, what should be the optimum load that you want to transfer, what should be the optimum gain. The second one, this incentivized load limiting, here they say that if the participant actually, if somebody participates in the program, then they are paying flat 100 rupees per month for that. And if you reduce your peak load during the, then per unit reduction you are getting 6 rupees. And there they have shown that if you if you keep your threshold close to the average, then most of the households will participate, again resulting to some greater incentive and higher savings rate. I will encourage all of you to go through this paper. This was published in Energy Journal in 2016, and this is one of the rare simulation studies based in the context of a very detailed data from a developing countries. We are going to stop with this paper, which was published by Wallach in 2011, followed by another paper in 2010. So here he is studying, the context of the study is a developed country, but the findings are very, very important. So they studied 1,245 households in the District of Columbia, and the data was collected almost 10 years back from 2008 to 2009, and they carried out a randomized control trial kind of an experiment where the control group, where there was a control group and there was a treatment group, and the treatment group received were exposed to sort of one of the instruments, hourly price, critical peak pricing, or the critical peak pricing with rebate. And it was observed that all these three dynamic pricing mechanisms, they actually provided very stable, predictable, and sizable demand reduction during the peak period. So all the mechanisms, it worked. What I find fascinating in the paper is the finding that we tend to believe that the customers who has high peak load, who has a lot of equipment, who has a lot of demand for electricity, the response only comes from their part. Those who are small users of electricity, they are not likely to respond to this kind of price or incentive based mechanisms. But this study actually proved this kind of a notion completely wrong. So in the District of Columbia, what they found that the response that they received to this kind of instruments from the low income households were much higher than what they received from the high income households. And the reason that they are giving was quite fascinating, because all these instruments, we always think about the shifting of the load, flattening of the load curve. So that is not the only thing which is being achieved. At the same time, as I mentioned, the households are actually experiencing some of the financial gains. So if your financial gain is 100 rupees, that may be a very meager amount for a very rich household, but that's a very important amount for a very poor household. So therefore, the response that came from the poor households, even if their electricity consumption was less, was much greater as compared to the high income household. This actually tells you that often we have a discussion that load shifting may not be a very efficient way of load management in the context of developing countries. But if this is the case, then the story may go other way around, and we may see a lot of response towards this kind of instruments in terms of load shifting in the context of developing country as well. We are going to stop here. In the next lecture, we are going to discuss about energy efficiency, which is our next tool that we are going to consider as a demand side management. Thank you and see you later.